Okay, good afternoon, everybody. How are you? This beautiful rainy day, right? Thank you for coming out. This is going to be a wonderful, wonderful discussion, and thanks everyone virtually for joining us as well. We're lucky to have with us a distinguished professor here at IU. You prefer Jerry instead of Jerome,
No,
right?
Jerome.
Jerome, sorry? Okay, Jerome, I'm so sorry.
Now that I'm older.
Absolutely. You've graduated to Jerome. I have nowhere to go.
Some of us only know you as Jerry.
There you go. Forget you heard Jerry. Jerome Busemeyer is a distinguished professor here in psychological and brain sciences in our world-renowned cognitive science program. He's also an adjunct professor in the Department of Applied Statistics. He's done a lot of amazing work over the years, a lot of interesting grants from NSF and NIH, which is really, really impressive. You're a member of the Society for Mathematical Psychology, the Psychometric Society, which sounds awesome. I'd love one of those t-shirts. Cognitive Neuroscience Society. It's a huge list here, so I won't be able to do justice to all of it. Today, though, we're going to be hearing about Jerome's work in quantum probability, applying quantum probability to judgment and decision-making models. Which I just find absolutely fascinating. I have to say, this is not an area that I knew much about, but as I dug in, I started to see pretty quickly some applications in a wide variety of contexts, including even this morning we were briefing a delegation from the EU on election security matters, and several of them brought up cognitive science questions, so I was able to refer to some of your work in that. So anyway, I look forward to this great discussion. Per usual, Jerome's going to take a little bit of time to brief us on the background, the lead up to this paper, and then we'll dig in from there. Okay, so without further ado, thank you so much for being here, Jerome. I really appreciate it. I'll get out of your way over here.
Well, I think the last time I was here was several years ago, and I used to come pretty often when Lynn was here and with Jimmy and everybody, but I haven't been here for a while.
Oh, yeah.
Last time I was here, the presentations were longer, so I have a long presentation. But what I'll do is I'll just present a short piece of it and open it up for discussions, because I guess you like to have more discussions and less presentations. So.
Everything's faster these days.
All right. But,
you can just tweet it out.
Yeah.
We'll have 140 character maximum.
So I'm gonna have. I'll start like.
But I know this is an area that a lot of us don't have a lot of background in, so if you wanted to take a little bit longer than normal to dig into it, I think that's fine. I think that's fair to say. So please feel free. Yeah.
Well, maybe I'll start from the beginning, and then if you
Yeah,
guys
I think
had
that's
enough,
fine.
just say okay. Well, first, what is the goal of our work? So, there's books like by Penrose and Hameroff has his colleague, not a book by Hameroff, but they have this quantum brain hypothesis, and we're not particularly interested in the quantum brain hypothesis. I mean, I would love the brain to be a quantum computer, but our work doesn't rely upon that. Maybe it's just a classical neural network model. So we're not building a physical, neurological, biological theory of the brain. And there's a lot of discussion of quantum related to consciousness, and that's a big philosophical issue in physics. And I think consciousness is a really interesting phenomenon, but we're not going to be talking about it's too difficult for me. So I work on simpler things like decision making. And so what we're doing, we're trying to use the mathematics of quantum theory, and we're applying it to behavior, primarily human judgment decision making. So anyway, I'll give you a brief introduction to quantum theory.
Yeah, that'd be great.
And like a 5-minute tutorial on quantum theory.
Yeah.
And maybe a little bit of evidence, and then we can go into more discussions, but at least one example to show you how we use the theory.
Please, yeah.
Now, you might ask why you're even doing this. Well, when I was growing up, I learned one probability theory. That's the one everybody learned. That's what we call Komagora probability theory, the classical probability theory. So I was surprised to learn that there's other probability theories out there. It's like, you grow up learning there's only one geometry, Euclidean, then you find out there's other geometries in the world. That kind of sparked my interest. So yes, and another thing is that human behavior, human judgment decisions, they don't obey these Kolmogorov axioms. And so we thought, well, let's take a look at this quantum probability as an alternative. Now you might say, well, that's kind of a shot in the dark. Why quantum theory? Well, one of the reasons why quantum theory might be a good idea, because it's built on the concept of non-commutativity. And the idea that questions, the ordering, sequencing of questions matters. When you ask one question, it sets up a context that later influences other questions. That's what the quantum physicists developed it for. Because when you measure particles, they're sensitive to the measurement. Well, humans are sensitive to measurement too, just like that. In fact, Bohr talked about the complementarity principle. That was actually borrowed from William James, who's a psychologist. Bohr had a friend named Reuben, who was Danish, and who knew William James, and Reuben introduced Bohr to William James's work, and so Bohr kind of borrowed the concept from William James. Now, Reuben was the guy with developed this impossible figure that's a woman that turns into a vase. Your brain kind of flips-flops. So we want to return, complementarity back to psychology where it came from. Another reason why we're interested in quantum theory, as you're going to see, is that it's a probability theory that's built on a vector space. Now, why is that important? Because a lot of the cognitive models, we like to use vector spaces. Neural network models, or even Bayesian models, well, not a Bayesian model necessarily, but neural networks definitely, are based upon vector spaces, so we're putting probabilities in a vector space. So, okay, so how do we use quantum theory? So I think this is the short paper I made a link to, which I think is kind of pretty reasonable and easy introduction. And so I'm going to go over a little bit of that paper. Anyway, we want to compare this classic Kolmogorov theory to von Neumann theory to see how these theories work. So this is our 5 or 10 minute lesson on quantum theory. So, and we're going to work with finite spaces just to make the mathematics simple. So imagine you got a survey and you've got you can rate a probability from 0 to 100 on integers, So you can give it 0, 1, 2, there's 101 possible answers, right? So if you're going to pick one of those answers, that would be an outcome, right? Like a survey response, you could pick a 93. That would be an outcome. And all those possible answers, that would be the sample space in a Kolmogorov theory. So the sample space would be all the possible answers. An outcome would just be one point in that sample space. Now the corresponding idea in quantum theory is we replace the sample space, which has like a cardinality of 101, with a vector space, which is a 101-dimensional vector space. And each orthogonal, basis vector or axis in this vector space would correspond to an outcome. Like 93 would be one basis vector, 94 would be another orthogonal one. So we have a 101-dimensional vector space instead of a sample space. That's how we're putting probabilities into a vector space. And now an event, like in Kolmogorov theory, an event is a subset, like an even number. That would be a subset of the sample space. And so this is where people often debate, like, where does quantum theory become quantum-like? And I think it's this line right here, because when you define events as subsets of a sample space, you're buying into a logic. You're buying into the logic of subsets, and the logic of subsets corresponds to Boolean logic. So like if A is an event, B is an event, then you have A and B is also an event. So you have closure, and the conjunction is defined in a commutative manner. A and B is the same as B and A. And you also have like a distributive axiom. A and, say, parentheses, B or not B is the same thing as A and B or A and not B. So you're buying all those axioms at one time when you buy the Kolmogorov theory. That's how logic of subsets work, that in a continuous space that leads to the sigma fields in probability theory. Well, in quantum theory, so this is the key idea. In quantum theory, an event is a subspace. So you're buying the logic of subspaces. So like even numbers, for counting 0, there'd be like 51-dimensional subspace, all the even numbers. Or if we looked at like the probability, if we looked at the event getting an answer between 25 and 30 inclusive, that would be 6-dimensional space, including the 25. So it's a subspace. So what you're buying then is you're buying into the idea that logic of subspaces. So it's a different logic. In fact, von Neumann invented a whole new logic called quantum logic. In fact, now there's all these generalized logics out there that are beyond quantum logic. But you're, in a way, you're relaxing some of the axioms of Boolean logic. Like, first of all, if A is an event in your vector space, like a subspace, and B is an event in your vector space, there may be no A and B. So you violate closure. And the reason why is because they're not commutative. Like you have an A and then B, and you have a B and then A, but you don't have any A and B because they depend on order. Also, the distributive axiom can break down. So the event A parentheses B or not A and B or not B is not necessarily in quantum theory distributive. It's not necessarily equal to A and B or A and not B. In fact, that's where this concept of superposition comes into play. So I often give an example, like my kids are grown up now, but like my son when he was young, let's say there's some event at school, and it could be, he could have done it or maybe didn't do it. So the event could be true that he did it or not true. So that's one event. And the event could be good or not good, like good or bad. Let's say good and not good. So in classic theory, if I think it's true that he did it, there's only two ways I could come to that conclusion. It's true and it was a good thing, or the other thing, possibility, only other possibility was true, it's a bad thing. Those are the only two thoughts I could have. But in quantum theory, if you decide it's true, you can stay unresolved about good or bad. I mean, it's kind of like this middle state, like where the law of exclusive middle is kind of violated. Because you can decide it's true, and you haven't decided if it's good or bad because you weren't asked about good or bad. So you're in what we call a superposition state with respect to good and bad. And so you're not in a true good state or a true bad state. So that's where the distributive axiom breaks down in quantum theory. Anyway, so we're relaxing some of the axioms, and so those relaxations I think are important for capturing cognition. Now, so another step here is, in Kolmogorov theory, in both theories we have something called a state. Like like if I'm giving probabilities that the person's going to give a higher rating, I'm going to give different probabilities than Jimmy. So we have different states. So we assign different probabilities. So in classic theory, you have this function P that assigns probabilities to all the subsets. Now, in quantum theory, it works a little differently. So this notation here is kind of easy to explain. I think it's easy to explain. But the idea in quantum theory is a little bit less direct. So in quantum theory, we have this vector space, and the state is a vector and sitting in the vector space. So this state represents your beliefs in a vector space. And so it's like if we had a 101-dimensional space, this S right here would be your state. It would be a 101 by 1 vector sitting in that space. And then this might be a question, like is it an even number, And so this P is like a projector. So it's going to project any state onto the subspace, like the subspace even numbers. Now this will be a matrix. So this will be a 101 by 1 vector. This will be a 101 by 101 matrix that just projects onto the subspace. So the product here, that's the projection. That's taking the state and projecting it on the subspace. So this projection is kind of like a match. How well does this, subspace, this, answer to a question match my state? It's kind of a match. And then we get the square length, and that's the probability. So how many people have computed this before in this room?
What, today?
Any time in your life, how many people have computed this? Everybody has.
Oh, there you go.
Well, I think everybody's probably computed this. Hasn't everybody performed linear regression? How many people have done linear regression? Everybody's done linear regression. So you've done this. Every time you do linear regression, this is what you do. Because if I have 101 subjects, then I got a vector that's 101 by 1 set of scores on something. And then if I have two predictors, two linear predictors, x1 and x2, I have a two-dimensional subspace. So I'm taking my 101-dimensional vector of scores and I'm projecting it onto the plane of my two predictors, and I get my prediction. So this product is my prediction, and then the R squared, because our vectors are normalized, it's kind of like working with z-scores. the R squared is this whole quantity here would be the R squared. So quantum theory is like computing R squares to compute probabilities. So that's how the quantum theory. There's only one more step, then we're finished with this lesson, and then we can go to an example. Then we can have discussions here. Now, of course, it's important, like for Bayesian reasoning and those kind of applications, to talk about conditional probabilities. So suppose we observe an event A, and now we want to revise our probabilities about B, knowing that A is true, or that we observe A. So in Kolmogorov theory, we construct a new probability function. Symbolize it this way. We take our old probability function and of B and A, and we normalize it by the probability of A. So that's our conditional probability definition. Quantum theory works similar. So the probability of B, given that we observe A, we start with our state, kind of like working in Polish notation or something, I guess. You work, but this way. So you start with your state. So we're talking about you've observed A first. Now we're looking at the probability of B. You start with your state. You project on A, and then you project on B. So and then you normalize, and that gives you the conditional probability. And so it looks similar to the Kolmogorov definition, except reduced commutativity. So in Kolmogorov theory, the probability of B and A is the same as the probability of A and B. There's no order effect. But in quantum theory, these projectors, these are matrices, and matrices don't always commute. Now sometimes they do commute, and sometimes they don't commute. So when these matrices commute, then it acts just like classical probability theory. But when they don't commute, that's when things become quantum, and you get order effects and context effects, and that's where the magic happens, when you have non-commutativity. Yeah, so in some ways, I could debate with this about some of my Kolmogorov fans, but in some ways, quantum theory is a generalization of classic theory because it introduces this idea of non-commutativity that you don't have in classical theory. If everything was commutative, then quantum theory would reduce to classical theory. So let's see how this just works with an example, but I'm going to skip over this one. I have a lot of interesting examples, actually. I can go back to some of them. But, this one's kind of a very popular example, and it illustrates the theory in a very simple way. How many people have heard of the conjunction fallacy? See? Oh, this is really famous result in cognitive science, the conjunction fallacy. So this was discovered by Tversky and Kahneman in 1983. Of course, Danny Kahneman, he's one of the Nobel Prize winners. I forget when. I think he won it with Vernon Smith. I think it was. Did he win it with Vernon Smith?
I don't think it was the same time.
No.
Well, anyway.
No, it wasn't a joint award.
I think he got a joint award with something.
Well, yeah, Kahneman got it with.
It's
It's going to come.
it's the S. It begins with an S. Oh, wow. Yeah. We'll go on. Check that later. Anyway, they've discovered the phenomena, but we built this quantum explanation for it. So here's the phenomena. So you're told a story like this. I mean, this is just one example, though. Don't get stuck on this one example, but this is an example. This is a famous example. So Linda was a philosophy major as a student at UC Berkeley, and she was an activist in social welfare movements. And this study was done in 1980, so anyway, imagine those days. So you got that information. So this.
He did share it with Smith.
What?
I just Googled it. He did share it with Vernon Smith.
Oh, yeah, Vernon
It's
Smith.
strange. Joint award,
But anyway, yeah, you told this story, so that gives you some information about Linda. So that generates your state, what you're going to believe. And so now you're asked to rate the probability of the following events. And this is when feminism was becoming really important and popular, I think, around 1980, maybe earlier, but anyway, you're asked, is Linda a feminist? Now you hear the story, that kind of makes some sense. Is Linda a bank teller? It doesn't make much sense, And so you're asked, is Linda a feminist and a bank teller? Is Linda a feminist or a bank teller? So you're asked all those questions. And you get these kind of answers. I mean, this is one study. So these are average results. I mean, Tversky did the study at Stanford. Stanford student. Now this is somebody else's study right here. But anyway, you get it with Stanford students. You get it with other universities. You get it with medical doctors. I mean, this is a very robust phenomenon. Now you don't always get it. If you ask me my age and my, where I work, you're not going to get a conjunction fallacy. But anyway, what we see here is that, it makes sense that you think there's no problem if you think it's not likely that Linda's a bank teller, but the problem is you think Linda's a feminist and a bank teller is more likely. So that's the conjunction fallacy. But you also get disjunction fallacy. So here's Linda's a feminist, and here's Linda's a feminist or a bank teller, and this is lower than that one. So you get both of these fallacies. In fact, they kind of correlate. So people that give one tend to get the other one. So, so this is an example where, the law, what we call the law of total probability is violated. This is one way to think about it. So here's the probability that Linda's a bank teller. Here's that she's a feminist and a bank teller, and here she's not a feminist and a bank teller. So these are two ways to be the bank teller. Of course, this first way is the conjunction that we're talking about. And this has to be positive or 0. So anyway, this right here has to be greater than that. Because, and the fact that they rate the conjunction higher, we're violating this total probability law. So here's how the quantum theory applies in this situation. But this is a toy model, by the way. So this is not the real theory. The real theory can be higher dimensional spaces. We don't really like to work in a two-dimensional space. It's too simple. You can disprove it very easily that it doesn't work. Actually, this little space here works pretty good, but there's some aspects, maybe I'll get to it later, that you don't want a two-dimensional model. Also, this is real. Now, generally, in quantum theory, these states can be complex valued states, but this is just real. And why we use complex values, I'll have to get into later. But anyway, so here's your state. So, and here's this ray right here represents, the basis vector way you would say, the ray represents saying yes to feminism. And so the orthogonal one represents saying no to feminism. So those are the two axes that you would use to judge feminism. And so notice that this is the yes to feminism, and here's your state, so you're close to the yes to feminism based on the story. Now the idea in quantum theory is sometimes you have like the event bank teller, what we say is non-commutative with feminism. We're going to assume this now. Now if it's non-commutative, what we're doing then is we're creating a new basis for judging bank teller by rotation. So the idea when things are non-commutative is we're changing the basis that we use to make judgments by a rotation. So it's kind of like you're looking at the world from the feminism view first, but then if you have to ask bank teller, you have to kind of switch your perspective and look at the world from a bank teller view. And if they're non-commutative, you can't think of both of them at the same time. Now it could be that maybe if you're trained, you would eventually learn to think about it both at the same time. But these are unusual questions, really. How often do you discuss feminism and bank teller? It's not like something you think about very much. You might have some kind of a world understanding of feminism, and you might have some kind of world understanding of bank teller, but you never think about the combinations. So you kind of build up a perspective for thinking about feminism and those kind of details. But then you think about occupations or bank teller, it's kind of a different perspective. So the idea in quantum theory, when things are non-commutative, we rotate the basis that we use to make the judgments. So here's the basis that we use for bank teller, right here, this red one. So this would be saying yes to bank teller, and this would be saying no to bank teller. So here's your state, and when we project to the yes to bank teller, it's very low, because the story. In fact, this projection, the squared length is 0.16. So here's, this is the projection right here on bank teller, that squared length is 0.16. Now, if we look at what's the probability that she's a feminist and a bank teller, then what we're going to do is we're going to first project on feminism and then project on bank teller. So we project to here and then we project to here. So that's the sequence of projections. And that sequence turns out to give you a projection right here, which is 0.3. Probability is 0.3, larger. So you can see how anyway, this simple two-dimensional model captures this conjunction fallacy very easily. The same exact picture will also capture the disjunction fallacy, but I'm not going to go through that detail. But now, a critical thing that you might have noticed, though, is the order matters. So, in other words, we're projecting on feminist first and then on Bank-Teller. And so that order gives you the conjunction fallacy. The other order doesn't. If you project on Bank-Teller first and then on feminism, it's going to be smaller than Bank-Teller, because the first projection would be on the Bank-Teller, and then on the feminism, that's going to be even smaller. So it's order dependent.
How do you decide what the angle is?
The angle?
Yeah.
Okay, well, I mean, in this case, we just rotated the, kind of fit the data, I mean, in general, these have to become parameters in a model. So in a model, when you're trying to fit a sequence of judgments, you're going to have to build a rotator that rotates, and then you have to estimate that parameter for the rotation.
In this particular example, how do you get to this particular angle?
Well, I just got to this angle because, I rotated this around so I would get, the conjunction fallacy. Well, I rotated around so I get both the conjunction fallacy and disjunction fallacy simultaneously. So I just, tried a rotation. And also I wanted to match the story. So this rotation is giving, feminism a high probability and Bank-Teller a low probability, which matches the story. And it also gives you the conjunction fallacy. It also gives you the disjunction fallacy. So anyway, this example, you can just play around with the angle here and rotate it around. Certain angles won't give you the result, and other angles will give you the result. So you pick the angle that you want. But of course, that is then you might say, well, then it's kind of post hoc because you're picking the angle after the fact. But anyway, I don't want to go into all these predictions here, but there are other predictions then that follow. So you can test the model in other stages. So it's not like it's not testable. In fact, our explanation has been tested. There's like a controversy going on right now, whether they've disproven our theory or not. Anyway, there's an alternative competing theory. We always have these competitions.
So can I ask a question? About
Yeah. So that's my presentation example. So I can open up for discussion now.
Great.
Can I ask just one
please.
question that follows
Oh,
up on his?
yeah.
his point?
And we'll get to Jimmy.
Yeah, so I noticed in the article on page 338 to 339,
Which article?
I'm sorry, it's the shorter one.
Yeah, okay.
Quantum cognition.
Yeah.
Because I had this question too about the rotation. There's a statement that under this section on order effects on attitudes, inference, and causal reasoning, and you say that it must hold for any rotation of the axes, and that's where I got confused. Why any rotation of the axes? Because I thought what you just described here was at some rotation it may hold, at some rotation it may not. So I was confused by the assertion there.
Yeah, well, there's another result that we get, maybe that you're referring to.
It was, it's on the section
Yeah, I think it's
on
related
order
to,
effects when you're getting into
Yeah.
Gore and Clinton and all of
Yeah,
that,
yeah,
and
that's-
then you're trying to generalize the discussion.
Yeah, that's this example. So, well, yeah, this is such an.
So I didn't know, I guess I wasn't sure how to interpret how generalizable. So my question related to the rotation of the axis on what he said here.
Okay, well, yeah, I have an answer to that, but first let me just
Okay.
kind of back up. So this is the Gore Clinton. Well,
Okay.
I changed this example instead of Gore Clinton to black. Do blacks dislike whites and do whites dislike blacks? I kind of like that example because these were asked by. This was actually asked in a Gallup poll along, 1990s, I think. But we also got the results at Ohio State. But anyway, so you're asked this question: Do whites dislike blacks? And like I'm a white person. If I'm asked that question, I have to think about it from my white perspective. Do I dislike blacks? But if I'm asked, do blacks dislike whites? I have to take myself out of my shoes and put myself in a black person's shoes. African American. And so you have to change your perspective. It's a change of perspective. You have to think of the world from your perspective, and then think of the world from another person's perspective. So we think that's a rotation, that change in perspective. And you can't do this simultaneously. So I can think about things from my perspective. I can't simultaneously think about it from somebody else's perspective. I have to do that sequentially. That's the intuition. Now, the way this model works, for example, this is an example where you say yes to whites dislike blacks, and then yes to blacks dislike whites. So this green one, this is the axis for yes, whites dislike blacks. And then this one right here is yes, blacks dislike whites. So if this is your state, you would first project on yes, whites dislike blacks, and then project on blacks dislike whites. And so you would get this square projection here, which is like 0.36 squared. But like if we go in the other order, if we first ask do blacks dislike whites, we project on that basis vector here, and then we project back up to whites dislike blacks, and that gives you 0.12. So that's just an example of an order effect. Now this example does depend upon the angle, like the particular numbers here, 0.36, 0.12, does depend upon the rotation angle. If we were actually at data, we'd have to fit that angle to fit this data. But what we were talking about being a very general property is this thing here. So this is a really strong test of that model. So in other words, here's our general model. So this is not two-dimensional. This could be 101-dimensional or anything you want. So we could be a really high-dimensional space, and we don't have to tell you what these projectors are in this derivation. So so that's the idea. We don't need to tell you what the angle is for this prediction here in this case. This is the prediction I'm going to get to. So we can have some arbitrary high-dimensional space and some projectors, but we're assuming they're non-commutative. So because we're the order effects. So like when we want to predict, let's probably say yes to A and then no to B, you start with your state, you first project on A, and then you project on no to B and get the square of length. What's the probability they say no to B and then yes to A? We first project on no to B and then yes to B. That's the whole theory. It's really simple. But there might be other couple little details. But using these two lines, well, pretty much these two lines, and not making any assumption about what the angle is, you can derive this theorem. So it's very general. So this theorem says, like, when the probabilities say yes to answer A and no to B in the AB order, plus the probability say no to A and then yes to B in the AB order, it has to equal, basically, the probability say yes to B and no to A in the BA order, plus the probability say no to B and yes to A. So this linear equality has to be 0. And that's true for any angle, any dimensional space, any initial state. So this is what's really general. It's a really general test of our theory. And so we tested this. And we have really pretty strong support for this this prediction about order effects. So that's the point that's the point we're making there.
Well, I thought though you said earlier it's like the classical is like a special case.
Well, the classical probability is a special case because like you get no order effects.
Exactly.
I mean, if there's no order effects, then this equality holds exactly because this would be the same as this. But if you're getting order effects and you still get this equality, that's when it's interesting.
Yeah. Jimmy, please.
So,
And then others if you want.
I'm still trying to understand Linda. I'm still trying to understand. So let me try the following. Suppose the students that answer this question, and so I'm going by the one in the paper, which is only the 2 parts. It says, which of the following is more probable?
Mm-hmm.
So what if the students who answer this question say, okay, the first one says Linda is a bank teller. So what if they say, okay, my population is women, and what's the percentage of bank tellers out there that are women? And then it's a small population, it's a small probability. So I said, that's a small probability. But what if going to the second one, what's more probable? Linda is a bank teller and is active in feminist movements. So what if I now change my reference point to within the group of all bank tellers, she's a feminist.
Well, that's a conditional probability.
That's what I'm. So
Yeah.
I'm trying to understand how these students are making a mistake based on classical probability. Where's the mistake coming in?
Yeah.
And it is. Are they changing reference points as they go from 1 to 2?
Well,
Which would be a sequencing effect. It may be different if you put this.
Well, if it's conditional, it will depend on sequence too, yeah.
Yeah.
But, they've asked people conjunction questions and conditional probability questions. You don't get the same answer. So the conditional probability question, they know that that's different than the conjunction question. They don't give you the same answer to those two.
So what's their response to why you get this phenomenon?
Well, when you point it out to them, most of them realize they made a mistake. But when you point it out
It's
to
not a
them,
mistake if you change your reference point.
well, it's a mistake. Well, like in your example, it would be a mistake when you're asked a joint probability question, you answer it with a conditional probability answer.
Yes.
That's a mistake.
Well, if they interpreted the question that way.
Well, it says and. It's like, what's the probability of this and this? It doesn't say what's the probability of this given
The question
this.
doesn't start off by saying, it doesn't, at least adhere. I'm not trying to be argumentative, I'm trying to understand. It doesn't lay out, okay. From going from 1 to 2, it doesn't say, in a sense, we're starting with the same reference point. Now, there's this group of bank tellers, and she could fit into that group. And now there's this group of bank tellers and feminists in that group. So clearly, if she's a bank teller feminist, she fits into the bank teller. That's clearly how you get the correct answer, right? But it seems like to me it's easy to see how the student's not presented in sort of a standard probabilistic model. It's not saying here's the set of all people that she might fit into in that sense. So.
Well, I mean, I don't know. It's like, and the Linda example is just one example. So another example would be.
I guess maybe we can go to the PD. That one's even harder for me to understand. The prisoner's dilemma, where you have the results from that. But
yeah, I can show you that example. It's really cool. But yeah, I mean, another example for the conjunction fallacy would be Bill is over 50 and he's a high executive businessman. What's the probability that Bill is over 50 and he's a high executive business? Let's see, how does it go? No, what's the probability? Like, I mean, maybe it's like this. Like, what's the probability that Bill had a heart attack? That's one probability.
okay.
What's the probability Bill is over 50 and had a heart attack? That's the other one. So over 50 and had a heart attack versus what's the probability that Bill's had a heart attack? Something like that. And you get a conjunction fallacy.
Yeah.
And even with doctors.
Because I have a feeling people are changing the reference point.
Well, I mean, if they're confusing a conditional probability with a joint probability, that's still a mistake.
Yeah.
I mean, because the word is and, not given. Or you're not told you're not told Linda is a bank teller. You're told what's the probability that either one of these things are true. So you're not told one is true and now what's the probability of the other one. You're told we don't know whether either one is true. What's the probability that they're both true? So anyway, but the conditional probability answers are different from the joint probability answers. So, you know, I don't think they're confusing the conditional with the joint. You get a different answer.
Okay.
But anyway, I mean, well, in the quantum sense, like it's maybe interpretation in the quantum way of thinking is that the concept of bank teller. This gets your reference point idea. The concept of bank teller, when you're only asked about bank teller, is not the same as your concept of bank teller when you're thinking about feminism. So it's kind of like when you're asking in the context of feminism, you're thinking about a different meaning of bank teller. Whereas when you're thinking about bank teller alone, you have a kind of a different meaning of bank teller. So the meaning of bank teller is contextualized by what it's paired with. That's how the quantum model works. So the quantum model, like if you first think she's a feminist, you're kind of like, you're no longer sitting on the Linda story alone. Now you're projected into this world where you're thinking about feminists, and you've got features about bank tellers in this feminist world, but it's not the same concept of bank tellers that you started with. So it's colored by the fact that you just answered feminism. That's
So, all right, last
Yeah.
you said they questioned these students on how they saw the problems. They were making mistakes more often, but did they give answers that might fit into quantum theory along the points that you
well, I
just
mean,
described?
to the extent they fit in quantum theory is the extent we can predict those answers using our quantum model.
Yeah.
So we can. I mean, of course, one little data point's not enough. So you have to have a larger experiment when you have lots of questions, and then we have to actually estimate parameters and try to see how well we could, use the model to predict the data and compare it to a competing model. So that gets into these kind of complexities.
Okay.
But there's this page I didn't go through, where we have a number of other qualitative predictions that don't depend on parameters. So there's a number, like one of them is order effects. So the order that you answer these questions about feminism and bank teller should matter. So if people do experiments and find that the order doesn't matter, that's what violates our theory. So that's where we actually have a controversy. One guy did an experiment, he's in Ireland, and he's a computer scientist, and he didn't get any order effects. But somebody else in France did the experiment, and they got order effects. And so it's like not clear whether exactly what the effect is there.
I think so. Yes, and then so then the back row.
Okay, so well, fascinating research. So it's I have just one comment. So there is a literature on physics and economics and quantum games. I think it would be interesting to make the connection with your research. So I was kind of reading their papers on games with complete information, Bayesian games with quantum, with a quantum approach. So I think that would be.
Yeah, the quantum game literature is interesting, and but there is a kind of a connection because we're using quantum theory and they're using quantum theory, but the quantum games allow the players to play quantum strategies, which requires a quantum computer.
Okay.
And so our theories only require quantum judgments, but it doesn't require a quantum computer.
Okay.
So that's the
it's
tricky
somehow
part.
connected to my second question that I think maybe is more interesting. It's when I read a little bit about quantum games, my immediate reaction was, well, now the strategy is even a more complicated object than it used to be in classical games.
Right.
Okay. And my feeling is, if I come back to and apply the same idea to your decision theory framework, it seems that the probability, the quantum probability, is somehow a more complicated object than the classical probability. And I understand if you use a theory to predict, you can always reproduce everything that you are doing with classical theory with quantum theory. Okay, but my feeling is, in some sense, can you reflect also that the quantum probabilities are a little bit more complex object? So in some sense, then the subjects or real people, they will, you capture this idea that they will be kind of, it's more flexible, the theory, but at the same time, it's more complicated, the theory. So it's,
I understand.
if you put that thing on the table,
Yeah, that's a good question.
still work for because I'm sure that in some cases classical probability theory works. If we add this complexity, is it the case that still the predictions using quantum theory will still work, or are we fixing the weird case and we are missing the standard one?
Yeah, well, that's a good question. So sometimes we're criticized. After all, quantum theory uses complex numbers, so it sounds complex. But it can use complex numbers. Yeah, but so to address that, in general, in cognitive science, maybe in machine learning, you have to do some kind of test of models that are sensitive to complexity, model complexity. And there's different ways of testing models sensitive to model complexity, but maybe one that I prefer and one many people argue for is a Bayes model comparison method. So in a Bayes model, sorry about my computer, I forgot that shit off my computer. In a Bayes model comparison, it's like you're getting the log likelihood of a model averaged across all the plausible parameter space. And then we're comparing that average log likelihood from one model to the average log likelihood to another model. So if a model is really complex, it's only fitting good because it's complex. It's got, it can really fit this little point over here, but it can't fit any other places very well. But if a model is like really fitting well everywhere in a space that's plausible, that the prior exists, then it does well. So that's the idea. So complexity would only work in a little teeny spot, not everywhere. And so we did and another application was with gambles, but there was this another violation of total probability that you get with gambles, and we compared prospect theory, which is a reference point theory, which changes reference point, which could explain these violations, and we compared it to our quantum theory. We did a Bayes factor comparison, and the quantum model still outperformed the prospect theory model. Actually, we had the same number of parameters, I think, in this model. We had two models. They both had 4 parameters, like a utility parameter and things like that. A loss aversion parameter, utility parameter, but they had the same number of parameters. But we used a quantum model to make predictions versus prospect theory, and the Bayes factor then supported the quantum model over the prospect. So it's a good question, though. I don't know what the answer would always be, but at least in that comparison, using the Bayesian comparison method, which many people think is a good way to adjust for complexity, our models still work better. Now, this one right here is a really strong test because it doesn't require any parameters. I mean, it's a very, of course, you know, when we need order effects. If there's no order effects, we don't get any difference between this and classical theory. Now, you can take classical theory, like, and introduce, like, classical theory, like, because the conjunction A and B is the same as B and A, you know, but you can fix it. You can post hoc stick something in there, like let's say you're like jury evidence. Let's say we get an order effect so that, you know, whoever presents last has a bigger impact. So if you have the order of prosecutor defense, you don't get the same answer as defense prosecutor. And so we model that with our quantum model. Now you can build a Bayesian model that says, well, and the Bayesian model wouldn't naturally do that because the probability of a hypothesis given A and B is the same as the probability of the hypothesis given B and A. So what you have to do is stick in there something else and say, well, the probability of the hypothesis given A and B when A comes first somehow makes A more important is not the same as the probability of the hypothesis of A and B when B comes first because now B becomes more important. Something like, you have to stick something like that in there. And you could do that post hoc. But then you're not going to satisfy this equality. And so how come this equality is satisfied? You know, if you make an ad hoc adjustment to the classical theory, there's no reason why this equality wouldn't be satisfied. But we find this to be satisfied. We had like we pulled out 70 national surveys from Pew National Research Surveys. There are a lot of questions like, you know, do you think the country's doing well? Do you like the president? Something like that, you know. And we found large order effects in these surveys, but we also found this QQ equality was largely satisfied. So, yeah. Anyway, anyway, that's my argument.
Wow, that's fascinating. Thank you. Yeah.
Okay.
And then Lee.
It's my first exposure to this topic, and so that's something I have to work with. But I'm curious. My question is, what does it add once I mention the following? In any population, even Stanford students, a portion of respondents may fail to follow Boolean logic. They may be tired, etc., whatever the reason is. Okay. It may be bigger in other populations, smaller in Stanford, among Stanford students, etc. I don't know. I can take any geometric forms, stick them on a screen, and make them add 0.1 or deduct 0.1 from the expected result from a strict rational choice model. It doesn't have to be the one you provide. I can play with ellipses and still come up with this if I can adjust the angles, you know, and the shape of the ellipses and all that. Anyone can with any form. So knowing both those facts, what does your model add that a simple sentence that says a proportion failed to understand Boolean logic within any population, and in the case of Stanford students is 0.1. What does that do?
Let's see. Well, I mean, let's see. I'm trying to think about how to answer your question. Well, like a couple of things came up in my mind when you're talking. I mean, first of all, like, of course, quantum model is making. If you can of course build other kind of geometric models to make predictions, but they might make terrible predictions. I mean, that's why we always have to compare how accurate are your predictions. I mean, if you take one little phenomena, which I only have time to present, you know, you can come up with 30 reasons for it. But then when you start getting lots of phenomena, or you get more than one judgment, you get a whole, you know, series of judgments that you have to predict. You can't just make up an arbitrary model. Only good models are going to work now. So you can't just, you know, make up an arbitrary model because it's going to break down as soon as you start testing it with more judgments. Now, like another question might be like, why are some people producing this conjunction fallacy, like, you know, and why are some not? Like, why is the percentage, you know, like, well, maybe the Stanford group, a large percentage of them produce the conjunction fallacy, like, I don't know, 60% or something like that. Why is it 60%? You know, we can't, with our quantum model, predict 60%, but we can explain maybe why there's individual differences. And so, in our idea, like, you know, if you have two concepts A and B, and you don't experience them together, so you've never had any kind of joint experience with them, so then all you can do is like work with one of those variables, and then think about it from the other variable. You don't have a joint space because you never experienced it. You never solved the joint probabilities. But if you had experience with those joint probabilities, then you can make the joint space. And so the individual difference comes from your experience with the joint events. So you have a joint probability. But if you don't have an experience with the joint events, you don't have a joint probability. So you have to construct it. And we think you construct it by this rotation. Now, why would it be 60% of the people need to do the rotation? Well, bank teller and feminism are two strange things. People don't encounter that very often. People have done experiments, though, with kind of arbitrary concepts. And like they've done experiments where you're trained on pairs of concepts, and then you don't make the conjunction fallacy. But if you only train on one concept at a time and then present it with pairs, you do make the conjunction fallacy. So there is something about experience in the pairs that's important for this conjunction fallacy. But why, what percentage, I can't predict exactly what percentage, but I can explain maybe why some people do and some people don't.
We're going to do a lightning round because we have a lot to get through without a lot of time. So we're going to do Lee, Sam, and Barb back to back. Okay? So Lee, go ahead.
Yeah, the conjunction fallacy seems to depend a bit on how firmly you hold those probabilities independently of one another. In other words, bank teller and feminist. And you talk here too, I mean, as if these are all probabilistic. But suppose they're really uncertain instead of probabilistic. You get the difference. So that,
I think that's important. I think the quantum model applies to the latter when things are uncertain.
Yeah, and
not relative frequencies in the world, but really like
correct.
There's no answer really.
Yeah, I think that's the point. And so for all of those decisions that have this relatively large element of uncertainty, so this seems very important for how you manipulate information flows to people to get a certain outcome.
Right.
So suppose you're in charge of this meeting. You know what outcome you want to get. You want us to say yes to some decision. So how you elicit information from us, the order in which you do it, it could be that, we all hold Jimmy in high regard.
Right.
So Jimmy says X. Suddenly I'm going to say, well, I was thinking Y. But maybe X is the way to go. And then someone else says X. You're going, Jesus, I was sure I was thinking Y. And well, I wasn't that sure, obviously. Otherwise, you'd never change. So it seems there's this literature in economics and political science about agenda control. And what agenda control seems to rely on is uncertainty. And this seems to capture that a lot better than a probabilistic world.
No, I think, first of all, I agree. I think this quantum theory is more relevant for what you might call uncertainty, where there is no relative frequency out there, where there's no right or wrong answer out there. It's a judgment call.
Yes.
And secondly, I think, I have a colleague. Well, second thing is we've actually done experiments where we ask you, or do you think we should, abortion should be, against the law, yes or no? And then we ask another question, and then we ask about abortion again, and we get situations where you'll change your mind. I forget what the intermediate. I have a slide here, but we have some intermediate questions. Like you may ask question A, then you ask question B, then you ask question A again, but B is what we call non-commutative. So what happens is you become resolved on A, so A, you got an answer like say A for sure. But now you're asked B. When you're asked B and you come up with an answer for B, you change your basis.
Right.
And now you're confused about A. So now you change your answer to A. And so we call that the ABA paradigm. And we do get these kind of changes in answers from an intermediate question when they're non-commutative. And the third thing, though, is I have a colleague, actually I sent in a proposal to your workshop to bring her over here because she's interested in these agenda effects. She has a theorem, I haven't read the whole paper, but she has a theorem that says, in quantum theory, if you're a quantum agent, there's a sequence of questions you can ask to get them to any state you want. That's interesting, By a certain sequence of projections, you can move them from an initial state to some other state that you want to get them to.
And this is what came up this morning, and we were talking about online misinformation campaigns, and this is where I was hoping that we'd have to be able to spend a little more time, because I think it's fascinating. This could be a really powerful tool, both for various sides, unfortunately.
So the kind of questions you ask can manipulate their uncertainty across.
I think we need to do a special session just on that. But just in the interest of time, let's try to do at least the last two. So Sam and Barb, perhaps if it's.
This is the first thing. seemed like there were some implications here for the way you structure voting methods and electoral systems.
Yeah.
So, do you rank order preferences, or do you decide to do rounds of voting, even though that's more costly?
Yeah.
That just seems like a really great avenue for.
Yeah, of course,
that
these
makes
survey, of course, the Clinton-Gore example is a good example, because Clinton wants Gore to go first because he looks better. They both look better when Gore goes first, But, so yeah, and so they want to be able to predict, what order they should go in, so that you get we had an example with Dole and Gingrich. These are all like Gallup poll surveys. The Dole and Gingrich, they both look worse, I think, when Dole went first. Or Gingrich went first. I think Gingrich went first. They both look worse. With the Clinton, they both look better when Gore goes first. So yeah, you want to know whether it's kind of like consistency effects and contrast effects going on in different surveys.
Were you asking about like first past the post vote and that kind of thing?
And
Like, more of a parliamentary system? Have you
I mean,
any
the different
studies on that?
procedures might produce different kinds of order effects.
Yeah.
I mean, rank ordering, I don't know what the order effects would be if you had to try to rank order, because you pick the best one, and then you got a context from the best one. Let's say now you got to pick the second best, but you've already decided on the best.
Yeah.
And so that produces a sequence.
That'd be a cool
So
study.
we haven't explored all these things, but that would be another interesting app. You could write a grant proposal on that.
See, there you go.
This ties in, there was a brief mention of like the prisoner's dilemma game and the different strategies that evolve, and you were talking about the strategic use of decision making and how this frames that better. So what I'm wondering is, for votes in representative bodies, or even just individual preferences, does the outcome matter? So if you know that your preference that you articulate, or the way you decide to act, cooperate, defect, however, it has an actual effect, but what if it's just like an expressive function? So you're in a body, 51 people have already voted against confirming this whomever to this position, and then in the alternative, how does it affect your articulation of preferences if the outcome has an effect or not? I'm wondering if that is something that can be captured in your model.
Oh, if the outcome, in other words, if there's a consequence from the outcome of the decision?
If you know there is not a consequence, if that's now a new piece of information.
Well, I mean, there's a couple answers to that. One is, it's good, when does in a quantum theory kind of sense, when does a measurement really take place? When do you really make up your mind so that you kind of project? Because I could ask, if you're a juror on a jury, and and you're just talking to other jury members, and people are kind of expressing, well, do you think he's guilty or innocent? And you feel a little bit of pressure from the other people, and you might give a judgment like, well, I'm pretty sure he's guilty, but maybe you feel pressured. You that might not be a real solid decision in your mind, and so that's not going to be a projection. So we might, they're what we call weak measurements in quantum theory. So you get some kind of a less than a real projection. But if you really make up your mind, so the judge says, look, you got to make up your mind, you got to resolve it in your mind. You think the person's guilty or not, so that you really resolve the issue and make a decision. Then I think we get this projection effect. And so if there's consequences involved, I think that's more likely you're going to have to make the decision and get a real projection. Whereas if there's no consequences, you can say something and it doesn't really reflect a real solid making up your mind kind of thing. It's just like a conjecture where you might change your mind in the next minute because it's not a really solid commitment to the answer. Yeah. So that's a good question about measurements, because when does a real measurement take place in our quantum models?
Yeah.
Quantum cognition.
That's a quick question.
Yeah. And if you'd like to wrap up with any comments from there, Jerome. Yeah.
I just have a quick question, is because when we do interdisciplinary research, sometimes words come to our mind, and sometimes I find different fields have different meanings to different words.
Sure.
So I just found curious, when I was reading the whole article, the phrase that kept popping up in my mind is, well, this is path dependence.
Yeah, right.
Is there? But I noted that the terminology path dependence wasn't in here, so I was just kind of curious why. To me, it's just like quantum is just another way of saying, well, obviously the system or the behavior is path dependent.
Yeah.
And of course, the challenge is in any given system that's path dependent is trying to determine what's causing the particular type of path dependence at issue. So I was just kind of curious why. I don't know if in your field they don't use that. I'm just saying that just poked at. So the fact that the lack of the phrase path dependence just stuck out for me, because in the areas that I do research where the equivalent order effects, everybody would be using the term path dependent. So I was just kind of curious
Yeah, well,
if that's correct. My understanding of path dependence is this is just another way of explaining.
This is path dependence, right? That's the main thing quantum is trying to get at, is path dependence.
Yeah.
And it's not the only way to model path dependence. We usually call it sequential effects, or order effects, sequential effects, path dependence. But and there's you can build, there's other systems like Markov systems. So Markov systems will also be path dependent. So a lot of our work we try to compare Markov models to quantum models because they're both path dependent, but then they make different predictions. In fact, the Markov model has this kind of law of total probability across paths because it obeys what we call the Chapman-Kolmogorov equation, which is effectively a kind of a law of total probability. So we can look at measurement effects and see how that differs from the quantum model. So the quantum model won't satisfy this Chapman-Kolmogorov equation. Anyway, but Markov models do produce path dependence, so we have to always try to compare the two. Because there are both ways of doing
So you're
this.
saying your quantum model does a better job explaining the nature of the path dependence in cognitive reasoning,
Yeah.
where the unit of analysis is the individual cognitive?
Yeah, that's what I would argue. Now, I have friends that do Markov models that would disagree. I mean, this is still
We'll have the
debatable.
next one.
But a lot of the work that we're finding evidence for our quantum model over a Markov model, but I can't say we're always the winner, So the Markov models are very powerful. That's a good way to model, sequential effects across time, path dependence.
Well, this has just been fascinating, and thank you for breaking it down so much for us. And do you have any final comments for the group, Jerome?
Well, I just really appreciate all the comments, and it's been fun to present the idea and get everybody interested in these ideas. I was a little bit surprised that I don't know if these people are going to like this, but it seems like it. Well, it seems like you like the thinking.
Well, please join me in thanking Jerome. Excellent presentation. And we'll see you guys next Monday or Wednesday for the research series. Is there anything else coming up? We just had Smart Pass.
Yeah. Research series.
Okay, good.
Not a lot going on.
So I was surprised at the date on the PD game.
Well, we also have a new data on
Well, you're from